Artificial intelligence is absolutely everywhere these days, but for a lot of us, it can feel like this mysterious black box, right? So in this explainer, we're going to pry that box open. We're going to uncover the core problems and the, frankly, brilliant breakthroughs that power all the AI you use every day. It's really a simple story of one problem getting solved, then another, and then another.
Okay, so let's kick things off with the most basic question of all. Why do we even talk about deep learning? I mean, why not just use a simple, shallow model? Well, the answer really gets to the very heart of why this whole field even exists, and it all started with a problem that the very first AI just couldn't crack. So, these first AI models were called perceptrons, and they immediately hit a wall with this surprisingly simple logic puzzle called XOR. It's a classic case where you just can't draw a single straight line to separate your data. A single layer is totally powerless. The solution? You got to stack them. You add more layers. Every new layer gives the network the ability, the capacity, to learn more and more complex patterns. To solve harder problems, we had to go deep.
So, okay, stacking layers sounds like a great idea, right? But it created this huge new problem. If a really deep network gets something wrong, how do you even begin to fix it? I mean, which one of the hundreds of layers is to blame? For the longest time, nobody had a good answer. There was just no practical way to train these giant, complicated structures.
And then came the big breakthrough, an incredibly elegant algorithm called backpropagation. Honestly, this is the engine that drives pretty much all of modern deep learning. Instead of just guessing, it gives you a mathematical way to assign blame. It starts at the very end, with the final mistake, and works its way backward, layer by layer, figuring out exactly how much each connection was responsible for that error.
Okay, so think of it like this. The network just took a test and failed. First step, you mark the final answer wrong. That's your error. Then, backpropagation goes to that last layer and says, hey, you were this much responsible for the mistake. That layer then passes the blame back to the layer before it, saying, okay, based on my error, here's your part of the blame. This chain reaction goes all the way back to the very first layer. And at each step, each connection gets a tiny nudge in the right direction. It's just a beautiful, super efficient way to learn from your mistakes.
So once we had backpropagation, things just exploded. After some early wins like Lynette recognizing handwriting, the real Big Bang moment, that was 2012. A model called AlexNet didn't just win the world's biggest image recognition contest, it absolutely demolished the competition. It was the proof everyone needed that deep networks were the future. But this huge success brought on huge new problems. The models were so deep now that they were unstable, and they loved to do something called overfitting.
Yeah, training these things became a real headache. They were super unstable. As data flowed from layer to layer, it would get all warped and shifted around, a problem called internal covariant shift, making it incredibly hard for the network to learn anything consistently. A really clever solution called batch normalization came along. Think of it as hitting a little reset button between each layer, forcing the data back into a standard shape. It just keeps the whole learning process smooth, stable, and way, way faster.
And then there was the other big problem, overfitting. That's when your model is basically just memorizing the test answers instead of actually learning the subject. The defense against this is a really clever technique called dropout. During training, it just randomly turns off a bunch of neurons. It's like training a basketball team, but for every practice, you randomly tell a couple of players to sit out. What happens? Everyone else has to step up, right? They become more capable on their own. That's exactly what dropout does to the neurons.
Okay, so we're feeling pretty good, right? We solved instability, we solved overfitting. And then, bam, we hit another wall. And this was maybe the biggest one yet. As researchers pushed to build even deeper networks, we're talking hundreds of layers deep, the error signal from backpropagation started to, well, vanish. By the time the signal got from the end of the network all the way back to the beginning, it was basically a whisper, nothing. The first layers, the most important ones, they weren't learning a single thing.
And the solution, which came from a model called ResNet, was just beautifully simple. It's genius. Look on the left, that's the old way. The signal goes through all these layers and gets weaker and weaker, kind of garbled. But now look at the right. ResNet added what's basically a shortcut, An information highway. This residual connection lets the original clean signal bypass all the complicated stuff and just get added back in at the end. It's a guarantee that the core message always gets through, making sure that gradient never, ever vanishes.
And this wasn't just some small fix. This was a total revolution. Residual connections completely flip the script, and they are a huge reason we can build the gigantic models that we see today. That barrier to going truly massive, it was finally broken.
So we've pretty much cracked the code for images. But what about language? You know, data where the order of things is everything. The dog chased the cat is a totally different universe from the cat chased the dog. This whole new challenge of understanding sequences, well, it needed a completely new kind of brain. So the first crack at this was the recurrent neural network, or RNN. The idea makes a lot of sense. It's a network with a little loop in it. It reads a word and then passes a bit of memory about that word on to the next step. But you guessed it, it had a fatal flaw. That same old vanishing gradient problem came roaring back, which basically gave the RNN a terrible short-term memory. It would forget the beginning of a long sentence by the time it got to the end.
So the fix for that was a much smarter kind of network unit called a long short-term memory, or LSTM. And this thing was literally designed to act more like a human memory. It has these internal gates that are constantly making decisions. There's a forget gate to throw out useless information, an input gate to let in important new stuff, and an output gate to decide what memory to pass along. This whole system let it hold on to context for much, much longer.
But even these powerful LSTMs, they still had this one major bottleneck. To understand the word it's looking at now, the model had to rely on this single, squished-down memory of everything that came before. I mean, imagine trying to write a detailed book report, but all you have to work with is a one-paragraph summary. You're going to miss the crucial details, right? This made it incredibly difficult for the model to link ideas that were really far apart in a long piece of text.
And then, in 2017, a paper drops with a title that was just perfect. It was part research statement, part epic marketing slogan. Attention is all you need. It laid out a radical new idea that would yet again change everything and kick off the era of the AIs we know today, like GPT.
So what in the world is this attention thing? Well, it's a mechanism that finally frees the model from just going one by one in a straight line. Instead of just remembering the last step, the model gets to look back at the entire input sentence all at once. It then calculates scores to figure out how relevant every single other word in the sentence is, creating these direct, powerful connections between ideas, no matter how far apart they are.
And what's so cool about this is how this one core idea, attention, which is the heart of the transformer, split off into two main families of models. First, you've got models like BERT. These are called encoder only. They look at the whole sentence at once, so they're amazing at understanding context, like for a search engine. Then you've got decoder-only models, like GPT. They work differently. They're all about predicting the very next word in a sequence, which makes them incredible at generating text. So let's just do a quick recap of this whole journey. It's really a story of one problem leading to one solution, over and over again. We needed deep layers to solve tough problems. Backpropagation was the engine that let us train them. When they got too deep and broke, ResNet's simple shortcuts fixed the vanishing gradient and allowed for massive scale. And finally, to really conquer language, the attention mechanism broke that final bottleneck of memory, leading us straight to the incredible AI we have today.
Each and every one of these breakthroughs was born from hitting a wall that seemed impossible to get past. This isn't just ancient history. These ideas are the living, breathing foundation of the AI that's probably in your pocket right now. And that same process, finding a roadblock and then discovering a genius way around it, is happening in labs all over the world as we speak. So that leaves us with one last thought. What's the bottleneck of today? What's the next great challenge that, once somebody cracks it, will unlock a whole new era of AI?